Ever felt like your fundamental understanding of reality was, really solid, like the ground under your feet, just stable and unchanging?
Mm-hmm.
Well, get ready for a pretty interesting trip, because on this deep dive, we're going to dig into how science has again and again challenged and reshaped what we thought were just obvious facts about the universe and, well, our place in it.
It really is quite a story. It shows how our deepest beliefs, the things we often just assume are universal truths, they're actually part of this interconnected system, what we call a worldview.
Right.
And we're going to see how these entire systems, these worldviews,
Yeah.
have been taken apart and rebuilt over centuries, often in ways that are, frankly, pretty surprising.
So our mission today is to explore that evolution, from ancient philosophy right up to the bleeding edge of modern science.
Yeah.
We'll trace these fascinating shifts in how we understand space, time, gravity, reality itself, even what it means to be human. You'll hear about concepts that might stretch your brain a little bit, and hopefully you'll get a shortcut to being genuinely well-informed on some of the biggest questions science is tackling. Okay, let's dive in.
Okay. So maybe we should start by clarifying what we actually mean by a worldview. Because it's not just, a random pile of beliefs.
Right, it's more structured.
Exactly.
Yeah.
Think of it like a system of beliefs interconnected, maybe like the pieces of a jigsaw puzzle. Each belief has to fit with the others, forming a coherent, consistent picture.
Ah, okay. So if you try to change just one piece, maybe pull out a belief from the middle.
Right.
It doesn't work. You have to change a lot of other connected pieces too. Like you end up having to build a whole new puzzle.
Precisely. And what's really fascinating here, I think, is that many of these beliefs, even the core ones, they often feel like obvious empirical facts, things you can just see or observe directly.
Like the sun rising.
Exactly. But they can actually be what we sometimes call philosophical or conceptual facts. These are really deeply ingrained assumptions about how the world must work, assumptions we often don't even realize we're making.
Interesting. Okay, so let's look at an old puzzle then. For centuries, like from about 300 BC to maybe 1600 AD, the main worldview in the West was largely Aristotelian, right?
That's right. That was the sort of default setting for reality for a very long time, a really comprehensive, stable picture for its era.
And what were the main pieces of that puzzle?
Well, at its core, it believed the Earth was at the absolute center of the universe. And it was stationary, didn't move.
Okay.
And then you had two regions. Objects below the moon, the sublunar region, they were made of four basic elements.
Right.
Earth, water, air, fire. And these were considered, imperfect, changeable.
Right. Things decay, fall apart down here.
Exactly. But beyond the moon, the superlunar region, so the moon itself, the sun, planets, stars, they're made of a fifth element called ether. And this was perfect, eternal, unchanging.
And here's the part that always gets me. The universe was seen as teleological. Is that the right word?
Yes, teleological.
Yeah.
It means things behaved the way they did because they had an essential nature and a natural goal or purpose.
So like a rock falls, not just because of gravity as we think of it now, but because its goal, its nature, is to return to the center of the universe, which was the Earth.
Precisely. And the stars moved in perfect circles because that was their essential nature and their goal in that perfect, unchanging superlunar realm. It's a fundamentally different way of thinking about cause and effect.
Totally different. And Ptolemy, around 150 AD, he really firmed this up with arguments, didn't he? Arguments for a stationary Earth.
He did. And they were very powerful arguments for the time. For instance, he argued, look, if the Earth spun, say, at 1,000 miles per hour at the equator.
Which it does, roughly.
Right. We should feel this constant massive wind like a hurricane blowing against the direction of rotation. But we don't.
Okay, makes
Or if the Earth orbited the sun at, something like 70,000 miles per hour, surely we'd feel something. Vibration, a constant gale. Again, nothing observed.
And the killer argument, for me anyway, was about throwing things up.
Yes, the dropped object argument. If you throw something straight up and the Earth is moving underneath it while it's in the air.
It should land somewhere else behind where you threw it from.
Exactly. But it always lands straight back down at your feet.
Which seemed like proof positive the Earth wasn't moving.
It really did. And add to that the lack of observed stellar parallax.
Explain that one quickly.
Okay, so if the Earth is orbiting the sun, then when we look at a nearby star from one side of the orbit and then 6 months later from the other side, its position against the background of very distant stars should appear to shift slightly, like holding your finger up and looking at it first with one eye, then the other.
Right, it seems to jump.
Yeah. But they couldn't detect any such shift for the stars. So either the Earth wasn't moving, or the stars were so incredibly, unimaginably far away that the shift was too small to measure.
And the second option just seemed absurd at the time.
It did. So these common sense arguments, they were logical, based on observation, and incredibly persuasive. They fit perfectly into that Aristotelian worldview puzzle.
But then came the early 1600s, and things started to wobble a bit. New evidence started putting cracks in that neat picture.
That's right. Very subtle cracks at first, but undeniable ones. And a key driver was the newly invented telescope, especially when Galileo pointed it towards the heavens. He saw things no one had seen before.
Like what? What did he see that caused problems?
Well, for one, he saw mountains and craters on the moon.
Which doesn't sound very perfect or smooth like the superlunar region was supposed to be.
Exactly. It challenged that core idea of perfect, unchanging heavenly bodies. Then he saw moons orbiting Jupiter.
So not everything revolved around the Earth.
Precisely. That was a big one. And maybe the most crucial observationally, was that he saw the full range of phases for Venus. Just like our moon goes through phases from new to full.
Why was that so important?
Because in the Ptolemaic Earth-centered system, Venus should only show crescent phases, never a full or nearly full phase from our perspective. But Galileo saw the full range. That directly contradicted Ptolemy.
But it fit perfectly if Venus orbited the sun inside Earth's orbit.
Exactly. There's a natural consequence of a sun-centered model. So these weren't just new facts. They were facts that actively didn't fit the old puzzle.
Now, Copernicus had actually proposed a sun-centered model earlier, right? But it didn't immediately take over.
Correct. Copernicus published in the mid-1500s. And what's often missed is that his model initially wasn't really simpler mathematically or even much more accurate at predicting planetary positions than Ptolemy's complex system.
So why bother with it then?
Because it offered a more natural explanation for certain things, like that retrograde motion, why planets sometimes seem to loop backwards in the sky, and why planets like Mars vary so much in brightness. Copernicus's model explained these things elegantly without needing lots of extra complex mechanisms like Ptolemy's epicycles.
Okay, so it had an aesthetic appeal, almost. Then Kepler came along.
Yes, Johannes Kepler took a huge conceptual leap. He was trying to make the Copernican model work better, but he finally had to abandon these centuries-old philosophical assumptions, beliefs in perfect circles in uniform, constant speed for planets.
So he threw out the perfect circles. What did he replace them with?
Ellipses. He showed planets move in elliptical orbits, not perfect circles, with the sun at one focus. And they don't move at a constant speed. They speed up when closer to the sun and slow down when farther away.
And this model worked.
Incredibly well. It was revolutionary, and suddenly the predictions matched observations with amazing accuracy. It was like finally realizing a puzzle piece wasn't round, but oval.
And then Isaac Newton, he kind of put it all together into a whole new system, a new science.
He absolutely did. Newton provided this revolutionary framework that changed the whole game. His 3 laws of motion, especially that first one, the principle of inertia.
The idea that an object in motion stays in motion unless something acts on it.
Right. Which sounds simple now, but it directly contradicted everyday experience, where friction and air resistance always make things stop unless you keep pushing them.
Yeah, you have to actively unlearn your intuition there.
You do. And then his law of universal gravitation, this idea of a mutual attractive force between all objects with mass. It explained why apples fall and why planets orbit.
But you mentioned even Newton struggled with it, the action at a distance part.
He did, deeply. How could the sun pull on the Earth across millions of miles of empty space with nothing apparently connecting them? It bothered him. Philosophically, he couldn't explain the underlying mechanism.
So what did he do?
He basically adopted what philosophers call an instrumentalist stance. He said, look, the math works, the equations predict phenomena perfectly, they fit the data. I frame no hypotheses about the ultimate cause of gravity, was his famous line. Essentially, it works, I can use it to predict things, but I don't really know how or why it works fundamentally.
Wow. Okay, so this new Newtonian worldview, this mechanistic picture of the universe as a giant clockwork machine, it really took hold, right? For like 2 centuries.
Oh, absolutely. From roughly 1700 to 1900, it was the dominant paradigm. It seemed like the final answer, explaining everything from the smallest particles, what they thought were the smallest particles, to the largest structures.
And it wasn't just astronomy that changed. You said it reshaped other sciences too.
Massively. Chemistry, for example. Lavoisier brought in quantitative methods, careful measurement, conservation of mass, moving it away from mystical alchemy towards a rigorous science. And Dalton's atomic theory pictured matter as composed of these tiny, predictable billiard balls, basically.
In biology.
Biology saw a shift away from vitalism, this idea that living things contain some special, non-physical life force. Instead, scientists started finding mechanistic explanations, like realizing nerve conduction was essentially an electrical phenomenon, or synthesizing organic compounds like urea from inorganic materials in the lab, showing there wasn't some unbridgeable gap between living and non-living matter.
Even things like electricity and magnetism, which seem kind of mysterious.
Right. They were initially just qualitative observations. But then figures like Coulomb and Faraday developed precise mathematical laws describing electrical forces and magnetic fields. And Faraday's discovery of electromagnetic induction, how changing magnetic fields create electric currents, well, that's the basis for pretty much all electric power generation today.
So by, say, 1900, the feeling was, we've basically figured it out.
There was a very strong sense of that, yes. A widespread feeling, perhaps best articulated by Lord Kelvin, that physics was essentially complete. All the main principles were known. There were just maybe, two small clouds on the horizon, a couple of minor experimental puzzles left to tidy up within the existing Newtonian framework.
Famous last words, right. Because those minor problems turned out to be not so minor.
Not minor at all. They were, in fact, subtle cracks that would eventually shatter that whole Newtonian machine and lead to entirely new revolutions in physics.
Okay, so what were these cracks? You mentioned the Michelson-Morley experiment. What was that about?
Right. So Newtonian physics, especially how it dealt with light waves, assumed that light, like sound waves needing air or water waves needing water, needed some medium to travel through. They called it the luminiferous ether.
The ether, right, this invisible substance filling all of space.
Exactly. So Michelson and Morley designed this incredibly clever experiment to detect the Earth's motion through this ether. As the Earth orbits the sun, it should be moving through the ether, creating a kind of ether wind.
Makes sense, like sticking your hand out of a moving car window.
Yeah. And they expected the speed of light measured in the direction of this ether wind to be different from the speed measured perpendicular to it.
Right.
The result was shocking. No difference whatsoever. No matter which direction they pointed their apparatus, the speed of light was always the same. It was like swimmers in a river, expecting to take different times swimming upstream versus downstream, but finding they always arrive at the exact same time. It completely contradicted the idea of a stationary ether.
Okay, that's one huge crack. What else?
Then there was a problem with black body radiation. That's the light emitted by heated objects. Classical physics predicted that these objects should emit an infinite amount of energy at high frequencies in the ultraviolet range.
Which obviously doesn't happen, or ovens would vaporize us.
Right. It was called the ultraviolet catastrophe because the theory failed so spectacularly at high frequencies. Also, when you heated specific elements, they didn't emit a smooth, continuous spectrum of light like a hot poker. They emitted light only at very specific discrete wavelengths or colors, like a fingerprint for each element.
And Newtonian physics couldn't explain why.
No idea. It was completely baffling within that framework. So these weren't just little anomalies you could tweak the theory to fix. They were fundamental challenges pointing towards something deeply wrong with the underlying assumptions.
And these unresolved issues, these clouds, they directly led to Einstein, right, and his theories of relativity.
They did. Relativity absolutely overturned these incredibly deep-seated beliefs, these philosophical or conceptual assumptions about space and time that went all the way back to the Greeks, even before Aristotle, and were just taken for granted within the Newtonian system.
Assumptions like?
Like the idea that time flows at the same rate for everyone, everywhere, a universal clock ticking away, and that objects have a fixed absolute length regardless of how they're moving. These feel like obvious empirical facts, don't they?
Yeah, totally intuitive. How could it be otherwise?
Well, Einstein showed it is otherwise. His special relativity, published in 1905, started from two simple-sounding postulates. One, the laws of physics are the same for all observers moving uniformly.
Okay.
And two, the speed of light in a vacuum is the same for all observers, regardless of their motion or the motion of the light source. That second one came straight from the Michelson-Morley result.
Right, the constant speed of light. But the consequences were huge.
Mind-bendingly huge. It leads directly to time dilation. Time literally passes more slowly for objects moving relative to you.
Wait, slower, like their clocks tick slower?
Their clocks tick slower, biological processes happen slower, everything. And length contraction objects moving relative to you appear shorter in the direction of their motion.
Sure.
Shorter. And perhaps the weirdest, the relativity of simultaneity. Events that appear simultaneous to one observer might not appear simultaneous to another observer who's moving relative to the first one.
Whoa, okay, that breaks my brain a little. There's no universal now.
Exactly. That's the profound implication. The idea of a single shared present moment across the universe just dissolves. It's observer-dependent.
So, why? Why does the universe work like this? It seems so unnecessarily complicated and weird.
Well, the deepest why we can really offer is simply because the postulates are true, because the speed of light is constant for everyone. If you accept that, these strange effects must follow logically. It's a powerful lesson that our common sense, our ingrained philosophical assumptions about how space and time should work, can be just plain wrong. The universe isn't obligated to make sense to us easily.
Okay, that's special relativity. Then came general relativity in 1916. What did that add?
General relativity was Einstein's theory of gravity, and it completely redefined it. Gravity, according to GR, is not an attractive force pulling objects together like Newton thought.
It's not a force. Then what is it?
It's a manifestation of the curvature of space-time itself. Massive objects, like the sun, actually warp or curve the fabric of space-time around them.
Okay. Like placing a heavy ball on a stretched rubber sheet. It creates a dip.
That's a classic analogy, yes. And other objects, like planets moving nearby, aren't being pulled by a force. They're just following the straightest possible path, what's called a geodesic, through that curved space-time. Their paths appear curved to us because space-time itself is curved.
So planets are just moving in straight lines through bent space.
Essentially, yes.
Yeah.
It's a radically different picture. And if we take general relativity seriously, as a realistic description of how gravity actually works.
Which experiments suggest we should?
Indeed. Then it forces us to see Newton's idea of gravity as a force as, well, maybe just an instrumentalist tool again. Incredibly useful for calculations in those situations, incredibly accurate. But maybe not what's really going on at the deepest level. That whole piece of the Newtonian puzzle, the force of gravity, gets replaced by the geometry of space-time.
Wow. Okay, so relativity fundamentally rewired our understanding of the big stuff, space-time, gravity. But then there's quantum theory, which deals with the really small stuff.
That's right. And if you thought relativity was weird and counterintuitive, well, quantum mechanics takes it to a whole new level. It completely demolishes our everyday common sense intuition about how reality works at the fundamental level.
Yeah.
It's like discovering the jigsaw pieces themselves can be fuzzy or exist in multiple states at once.
Okay, I'm braced. But you mentioned it's important to distinguish things here.
Yes, crucially. We need to separate the quantum facts, the actual results we get from experiments, which are undeniable from the quantum mathematics, the equations, like Schrödinger's equation, that describe those results with astonishing precision, and then from the various interpretations of what that math actually means about the nature of reality. And those interpretations are wildly different and still hotly debated.
Got it. Facts, math, interpretation. So what's a key quantum fact? The famous one is the two-slit experiment, right?
That's the classic, yeah. So imagine you fired tiny particles, like electrons, one at a time towards a barrier with two narrow slits in it. Behind the barrier is a detector screen.
Okay. If they're particles, you'd expect two clumps on the screen, right behind the slits.
Exactly. But that's not what happens. If you just let the electrons go through without watching which slit they use, they create an interference pattern on the screen, alternating bands of many electrons and few electrons. That pattern is characteristic of waves interfering with each other, like waterways passing through two openings.
So the electrons are acting like waves even though you fire them one by one? As if each electron somehow goes through both slits at once and interferes with itself.
It appears that way. But here's the really weird part. If you place a detector at the slits to see which slit each electron actually goes through.
To catch it in the act.
Right. As soon as you do that, the interference pattern vanishes. Now, you do just get two clumps behind the slits, as if the electrons behave like simple particles all along.
Whoa, so just looking at which path it takes changes its behavior from wave-like to particle-like.
It seems so. The very act of measurement, of observation, fundamentally alters the outcome. It's incredibly bizarre and counterintuitive.
That leads to things like Schrödinger's cat, doesn't it? The cat that's both alive and dead.
Exactly. That thought experiment highlights what's called the measurement problem. How does an entity existing in a superposition of multiple possibilities, like the electron going through both slits, or the cat being both alive and dead, suddenly collapse into one definite state upon measurement? What constitutes a measurement? Does consciousness play a role? These are huge questions.
And the interpretations try to answer this.
They try. The standard, or Copenhagen interpretation, basically says, don't ask what the electron is before you measure it. Quantum entities simply don't have definite properties like position or momentum until they are measured. It's not just that we don't know them, they are fundamentally indeterminate.
That feels unsatisfying somehow.
For many, yes. Another prominent one is the many worlds interpretation. It says there's no collapse. Instead, every time a quantum measurement happens, all possible outcomes occur. But each outcome happens in a separate, parallel universe that branches off from ours.
So there's a universe where the electron went through the left slit, and another where it went through the right, and infinite universes splitting off constantly.
According to many worlds, yes. An unimaginable number of parallel realities with different versions of you existing in many of them, having made different quantum choices along the way.
Okay, that's a lot to take in. But you also mentioned something called non-locality, Bell's theorem and experiments proving something spooky.
Ah, yes. This is another mind-bender, maybe even more fundamental. Experiments based on work by John Bell, like those done by Elaine Aspect and others, have experimentally confirmed what Einstein famously called spooky action at a distance.
What does that mean practically?
It means that if you have two quantum particles, say electrons, that are created together in a special entangled state, they remain connected in some way, no matter how far apart they travel. If you then measure a property of one particle, say its spin, you instantly know the corresponding property of the other particle, even if it's light years away.
Instantly. Faster than light.
The influence seems to be instantaneous. Measuring one particle seems to instantaneously affect the state of the other, far faster than light could travel between them. Now, this doesn't mean we can use it to send faster-than-light messages. That's a common misconception. You still need classical communication to compare the results.
But it tells us something deep about reality.
It tells us reality is non-local. Things are connected in ways that defy our intuition about cause and effect, only propagating locally through space. There are correlations, connections between distant events that aren't mediated by any known force or signal traveling between them. It fundamentally challenges the idea that reality is made up of separate objects only interacting when they're close. It's profoundly strange.
Okay, so physics completely rewrote the rulebook for space, time, matter, energy, causality. Meanwhile, in biology, another revolution was happening with evolution. How did that reshape our worldview?
Evolution by natural selection, primarily developed by Darwin and Wallace, offered a completely new way to understand the history and diversity of life, including ourselves. And it challenged some very deep-seated assumptions about purpose and our place in the cosmos.
The core idea is pretty simple, right? Variation and selection.
Deceptively simple, yes. You need three things. First, variation individuals within a population differ in their traits, and these traits can be inherited. Second, a struggle for existence. More individuals are born than can possibly survive and reproduce, leading to competition. And third, differential survival and reproduction. Individuals with variations that make them better suited to their environment are more likely to survive and leave more offspring.
And over time, the favorable traits become more common.
Exactly. That's natural selection. Over long periods, this process can lead to significant changes within species, and eventually the emergence of new species. You can even see the principle working metaphorically in things like the evolution of technology. Early cell phones competed, variations arose, and the ones with fitter features, like screens and apps, eventually dominated.
But it's crucial to understand what evolution isn't, right? Like it's not aiming for anything.
Absolutely critical. Evolution is not a goal-directed process. There's no predetermined path, no ladder of progress leading towards complexity or humans. There are no inherently higher or lower species in a biological sense. We, humans, are not the intended final product of evolution.
Our existence is more contingent, dependent on chance events.
Profoundly shaped by chance, yes. Think about the asteroid that wiped out the dinosaurs 66 million years ago. If that hadn't happened, mammals might never have diversified, and creatures like us almost certainly wouldn't exist. We're one twig on an enormous, constantly branching bush of life, shaped by adaptation and a lot of historical accidents.
And just a theory line. How do scientists respond to that?
Well, in science, a theory is the highest level of understanding we have. It's a well-substantiated explanation of some aspect of the natural world based on a vast body of evidence that's been repeatedly tested and confirmed.
So it's not a guess.
Not at all. It's the most powerful explanation we have for the patterns of life. It's in a totally different category from, say, string theory in physics, which is currently much more speculative and lacks direct experimental evidence. Evolution is a cornerstone of modern biology, supported by evidence from fossils, genetics, anatomy, biogeography, you name it.
I think a key realization for many people is about our relationship to apes. We didn't evolve from chimps, right?
Correct. That's a common misunderstanding. We didn't evolve from the apes that are alive today. Instead, humans and modern apes, like chimpanzees, gorillas, share a common ancestor that lived millions of years ago. We're evolutionary cousins, not parent and child.
And tracing that back further.
We share common ancestors with all mammals, then all vertebrates, then all animals. And ultimately, if you go back far enough, about 3.5 billion years or so, we share a common ancestor with every living thing on Earth. Bacteria, fungi, plants, us. We're all related, part of one single tree of life. That really changes your perspective.
It does. Now, evolution obviously has huge implications for things like religion and morality, too. The design argument, for instance.
Yes, the idea, famously put by William Paley with his watchmaker analogy, if you find a complex watch, you infer a watchmaker that the intricate design of living organisms implies a divine designer. This is a very powerful argument for centuries.
But natural selection provides an alternative explanation for that complexity.
It does. Natural selection, acting over vast timescales without foresight or purpose, can produce incredibly complex adaptations that look designed. This obviously led to major debates. Can traditional religious beliefs, especially literal interpretations of creation stories, coexist with evolution?
And the answers vary.
Hugely. Some argue they are fundamentally incompatible. Others, like the theologian John Haught you mentioned, propose different ways of thinking about God. Maybe God isn't a tinkerer who designed every detail beforehand, but is involved in the universe's ongoing, unfolding, evolving processes. It's called process theology. So there are ways people reconcile these ideas, though not without challenges.
What about morality? If we're just products of evolution, where do right and wrong come from? Does evolution explain ethics away?
That's one of the most fascinating and debated areas. Evolution can certainly help explain why we have moral intuitions. Studies using game theory, like the iterated prisoner's dilemma, show how cooperation and niceness can evolve as successful strategies, even out of self-interest.
Because cooperation pays off in the long run.
Often, yes.
Yeah.
And experiments like the ultimatum game, where people will reject an unfair offer of splitting money, even if it means getting nothing themselves, suggest we have an evolved, innate sense of fairness, or at least an aversion to unfairness. It seems to be a human universal.
So evolution explains the origins of our moral feelings. But does that mean morality is just subjective, an evolutionary trick?
That's the big philosophical jump. Can we get from is, how we evolved, to ought, how we should behave? Philosophers like Michael Ruse argue that evolution explains why morality feels objective and binding to us, because having such strong feelings promoted cooperation and survival for our ancestors.
So the feeling of objectivity is real, but its source is evolution.
According to Ruse, yes. The feeling that morality is objective is an illusion foisted upon us by our genes to make us good social cooperators. Morality isn't written into the fabric of the universe. It's written into human nature by natural selection.
That's a pretty profound thought, that our deepest sense of right and wrong might be a biological adaptation.
It is. It challenges many traditional views, suggesting morality is human-based, not derived from divine commands or abstract universal principles. It's a perspective that evolution forces us to consider.
Okay, so we've come a long way from Aristotle's purposeful, earth-centered organism of a universe to Newton's grand, predictable clockwork machine.
Right.
But where does that leave us today? What's the metaphor now? It seems like modern science has kind of broken the metaphors.
I think that's a great way to put it. Modern science, especially relativity and quantum mechanics, forces us to confront a reality that just doesn't fit neatly into a simple, comforting picture or metaphor anymore.
Yeah.
Relativity, as we saw, showed that things we absolutely took for granted as obvious empirical facts, the uniformity of time, the fixedness of space, were actually these deeply embedded philosophical assumptions. And they were wrong. That's a huge lesson in intellectual humility right there.
And quantum theory reveals this bizarre world at the smallest scales with indeterminacy, observer effects, and the spooky non-locality instantaneous connections across space. It's not like anything in our everyday experience.
Not at all. And then evolution paints a picture of a universe without inherent purpose, without a predetermined goal, where humans are not some pinnacle of creation, but one outcome of countless chance events and natural processes acting over immense timescales.
So maybe the biggest takeaway isn't just the specific beliefs that changed Earth-centered to sun-centered, force of gravity to curved space-time, design life to evolved life.
Right. It's more about the process. It's about how science continually forces us to re-examine our most fundamental assumptions. It makes us question the very basis of our confidence in what seems obvious or common sense.
It constantly challenges those philosophical or conceptual facts we didn't even know we had.
Exactly. And that raises, I think, a really important final question for everyone listening.
Which is?
What deeply held belief do you have about the world? Something that feels like an undeniable, obvious, empirical fact that might actually be just another one of those philosophical or conceptual assumptions. What bedrock truth might be the next one that science shows is, well, not quite right, or maybe completely wrong.
What assumptions are we making now that future discoveries will overturn?
Precisely. Because this deep dive into understanding the universe, it's never really finished. It's an ongoing journey of discovery and revision. And honestly, that constant potential for surprise, for finding out reality, is even stranger and more wonderful than we imagined. That's the most exciting part.